Okay, so welcome everybody. The first speaker of this morning's session is Gang Yang. We'll be talking about making spurious poles real via double copy. Please.
Okay, yeah. So I first like to thank the organizers for their invitation. So today I'm going to talk about some recent work, mainly about color kinematic duality and double copy for form factors. And this work are based on the work with undergraduate students, Guanda Lin, and also together with another graduate student, Siyuan Zhang. Okay, so the talk is divided mainly in 3 parts. I will first give an introduction for some backgrounds. Then I will talk about some high loop CK dual solutions for form factors. And finally, about the double copy picture for form factors. So we know that despite the very different nature, there has been no connections between the gravity and the gauge series. The very famous one is this the holographic principle, which is really a duality, an equivalence between a gravity and a gauge theory. There's also a known relation, this is so-called double copy relation between gravity and the gauge series. And this will be the main topic about this talk. So the underlying picture is also easy to understand, as one can see that gravity is a spin 2 particle. Okay, so a spin 2 particle it's highly possible that one can make a double copy of this spin 1, which is the gauge theory. Also in the string theory picture, a closed string can be decomposed as 2 open string. So to concretely realize the picture, of course, is quite non-trivial. Fortunately, there has been several formalisms, including the KLT relation and the BCJ relation, and also this the CHY formalism. So our talk will mostly regarding this BCJ relation, also which is the main theme of this workshop. So the first about the double copy duality. This is a remarkable duality about the color factors and the kinematic factors. So the color factor is related to the gauge symmetry, which is the internal symmetry of the theory, while kinematic factor is more close to the space-time symmetry. So the duality between these two factors are actually quite surprising. And to just review a simple example, one can consider this for loop amplitudes. So the idea is to write the amplitudes in terms of the triversion diagrams. And in this case, one has only 3 diagrams. So the color factors, the C, and the propagators are determined by the topology of the diagrams. The intrinsic physical information is actually contained in the kinematical numerator, the N here. The non-trivial requirement here is to ask these numerators, kinematical numerators, satisfy the same algebra relation as the color factors. So which is named as dual Jacobi relation here. So in general, certainly this is a very non-trivial requirement. An important bonus about this duality is once one can construct a gauge amplitude to satisfy this duality, it is straightforward to obtain the gravity amplitudes by simply replacing the color factor by another copy of the kinematical factors, which in this case, you get the for gravity amplitudes. So certainly there's many ways to understand why this is true. Here, I just want to emphasize from this the diffeomorphic invariance point of view. So the gauge invariance for the gauge amplitudes via the double copy actually implies the diffeomorphic invariance in gravity, which shows why this double copy procedure makes sense. Okay, so So in the gauge side, one can make a gauge transformation, which is basically deform your numerator by this delta here. And the gauge invariance, of course, ensure that this the amplitude is invariant. Thus give this the relation, which is diffeomorphism is actually equal to 0. Here, the relations between color factors are, of course, play an important role here. And thanks to the color chimera duality, one can replace this color factor by a set of another numerators, as long as they satisfy the same relation. This vanishing condition doesn't change. Okay, and this vanishing condition actually is related to the deforming invariance of the gravity. Okay, so this picture can be generalized also to high loops. For example, given a high loop amplitude, one can obtain the high loop gravity amplitudes. Okay, just to give another summarize, the color chimera duality, which plays an important role here, is within the gauge theory. Okay, it's a duality between the color factors and the kinematic factors, and this duality, of course, has been understood at tree level. However, in general loop level, it's still conjecture. And given this duality, one can make a connection between gauge and gravity theory. This step is through the so-called double copy procedure. So it's a powerful, in a sense, one can understand the very complicated gravity theory by studying a simpler gauge theory. Of course, because the CK duality is a conjecture, it is usually very non-trivial, and a priori you don't know whether such a solution exists. So it's a main challenge actually in this whole picture. So the topic of this talk will consider this picture for a particular class of observables called form factor. So the form factor are defined as a matrix element between unshelled states and a local operator, which is formally given by this formula. You have this the operator inserted here, and by Fourier transformation, one can go fully into the momentum space. Because of this operator, the form factor is partially on shell as well as partially off shell. It can be taken as a bridge connecting the world of amplitudes as well as correlation functions. There's many talks about the EFT in this workshop. Actually, the operator considered here can be understood as the interaction vertices in the EFT. To give an example, which is closely related to this to the form factor we consider in this talk, we consider this Higgs effective theory, which is obtained by integrate out this heavy top quark loop. Okay, so Higgs has no direct interaction with gluons, but in this effective theory, when after integrating out the top quark loop, one obtains the Higgs gluon effective vertices. So if one compute a Higgs gluon amplitude in Higgs effective theory, the amplitude is precisely equivalent to the form factor we defined in the previous page, where the operator is taken as this the interaction vertices. Okay, so having this background, let's go to the topic of about the color chimera duality of form factors. To have a concrete setup, we will consider this 3-point form factor of stress tensor multiplied in superior mules. And as also mentioned previously, this has a connection to the Higgs to 3 gluon amplitudes in QCD. And even surprisingly, this the relation can be made more precise, that inspired by this so-called maximum transcendentality principle, so far has been checked up to two loop level that Yang-Mills results give precisely the maximum transcendental parts of the QCD Higgs to gluon amplitudes. So potentially this the results in Kuznetsov superior mules may have also had the phenomenological application in this sense. So let's just briefly review this as a well-known procedure for the loop construction via CK duality. So the first step is to use the CK duality as an ansatz which allows you to construct a compact answers for your loop integrand. And this loop integrand will depends on certain free parameters, actually linear depends on them. And so to fix these parameters in the answers, one can apply various physical constraints. Of course, the most important one is this so-called unitary cards. So, so at a technical level, this the whole strategy is actually to solve a linear algebra problem. However, the main difficulty of the challenge is that because your input is based on a duality, so CK duality is based on a conjecture. So it's a priori not known whether the solution exists. So it would be a problem if you cannot find a solution, okay, whether you make a mistake or you have to enlarge your answers. So to give a concrete example, we apply this strategy to the three loop this Higgs three loop 3-point form factor. So there are in equal mills, you can exclude those sub-bubble or sub-triangle diagrams, and there are this about the 30 diagram to consider. And using the CK duality, one impose a non-trivial dual Jacobi for these numerators, and it turns out that one can only consider two numerators as master graphs. Once you know the numerator of these two graphs, you know all of them through this dual Jacobi relation. In this way, one gets answers with about 300 parameters. Next, we need to solve these parameters by imposing various constraints, including the symmetry constraints, as well as the unitary cards. The unitary cards, basically, you cut your loop quantity in terms of a product of tree quantities, and you check their consistency between the two expressions. And after checking all possible unitary cards, we find a solution that there is still lie in a 24-dimensional solution space. Okay. Of course, your final physical answer is independent of this the free parameters. Actually, even at the integral level, if you perform simplification, these free parameters cancel. Okay, this is just a consistent check. To give a non-trivial example, actually, which is announced today on arXiv, we also complete the for-loop computation. In this case, involve about 300 trivalent diagrams, and there are 4 master topologies to consider. And also solving this parameter by imposing unitary cards, one finally find a solution with surprisingly more than 100 free parameters. Also, you can check that after simplification, this free parameter cancels. However, the point here is that you start from answers satisfy CK duality. So it means that the solution with these free parameters still preserve this CK duality structure. That's a non-trivial thing. To summarize, this is a table provide a summarize for the 3-point form factor up to 4 loops. Okay. The most important information is about the growth of the free parameters in your final solution. We see that it grows actually quickly. As you increase the loop level, the solution goes to even larger solution space. So this is a feature very different from the so far the known case for amplitudes. For example, we know that for the five loop 4-point amplitudes, it has been extremely difficult to find a solution. So in this sense, it's highly promising to go to even higher loops for form factors. Okay. And given this the high loop integrand, we also study the hidden structure, and we can, in this case, we identify a precise dual conformal symmetry. Let me just give what's the precise meaning of this symmetry. We take this the light-like limit for the off-shell operator leg. Okay. So and then one consider this okay, so first this one can impose the dual momentum space based on this periodical Willis line for the form factor. Okay, so this you have 3 on-shell momentums plus the off-shell operator. You take the light-like limit for this Q. Then you do a conformal transformation in this dual momentum space. Okay, and you consider a particular direction, that is a conformal boost along this Q direction, then you find your integrand is precisely 0. So I will not go into further details. It's also given in this paper. I just want to highlight this. Even for planar form factor, this symmetry is not so trivial because your planar form factor involving non-planar integrals. This is just a two-loop example. You have this cross box, which is in amplitudes only it appear in the non-planar 4-point amplitudes. Okay, in the for-loop case, it's you have much more dozens of these non-trivial non-planar topologies. Okay. So in the remaining time, let's go to consider this double copy of form factors. So in particular, we have talked about the CK duality and it's natural to ask whether double copy can be also applied. First, we have to make this problem clear by asking this question: what is the consistent gravity observable? Of course, the gravity observable should preserve the deformed invariance, similar to the gauge amplitude should preserve gauge symmetry. In this sense, that you make a deformation for your polar vector of graviton, it should be 0. For form factors, the new feature is that you have an insertion of a local operator. So it seems to have a puzzle here. So the double copy, how to make a double copy for a local operator is not obvious in gravity. In some sense, that the local quantity in gravity would break the deforming invariance in a gravity theory. So this just shows that it's not so obvious how to make a double copy for the form factor involving a local operator. And the solution that we found involve a very intriguing feature. So here just one very intriguing feature I highlight here, that certain Spurious-Poles in the gauge theory. Okay, so for the gauge form factor is a Spurious-Pole. However, after double copy, it becomes a real propagator in the gravity. So the solution extends out that you still impose the CK duality. However, you should not be afraid of the Spurious-Poles in your construction. Okay, so the mechanism seems intriguing. I will try to explain this using the very simple example. It's probably even simpler than the 4-point amplitudes. Okay, so let's consider the 3-point form factor involving an operator which is trace phi square. You can consider a Yang-Mills theory with a adjoint scalar in your theory. Then you have a local gauging event operator, which is phi square. Then your on-shell states contain 2 scalars and 1 gluons. Okay. There are 2 Feynman diagrams, 2 trivalent diagrams, given by the graviton coupling to each of the scalar legs. Okay. And the result is given by 2 terms. Because this operator is a color singlet, both of them share the same color factor, is FABC, F a struct constant here. You can do a simple Feynman diagram computation, which is given by only by this gluon scalar interaction vertex, which is given by this results. Then if you naively make a double copy, you get a very simple answer. Okay. However, this answer is not well defined in gravity in the sense that it breaks the deforming invariance. If you take this the epsilon 3 as a graviton polarion vector. So how to make this well defined? It's similar to amplitudes. We impose the CK duality. Of course, the duality here is no longer the Jacobi relation. It's because that your operator in different positions doesn't change your color factor. You impose that the numerator should satisfy the same relation as your color factor, which is trivially equal with each other. And in this case, it's not hard to find that there is only a unique solution, okay, which is given by a color-ordered form factor times a rational factor given by the Mandelstam variables. So the numerator now is manifest the gauge invariant. Okay, so if you make a double copy, it's actually also manifest the deforming invariance for this double copy quantity. Okay. However, the point is that the numerator has a Spurious-Pole. Okay, you can see that the introduced Spurious-Pole. This Spurious-Pole, if you plug in this numerator in this gauge form factor, it cancels because you have an extra numerator S1 3 plus S2 3, which will cancel this Spurious-Poles. So it's really a Spurious-Pole for gauge form factor. However, if you do a double copy, the numerator can only cancel one of the poles. You still have left a pole, which is at least it become a real pole in this double copy quantity. Okay. So this actually makes make one worry about whether this is consistent.
You have 10 minutes now.
Okay, thank you. There's a nice feature very nice feature that if you boldly enough to check this factorization, you find that this G3 has a nice factorizing behavior under this new Spurious-Poles. Okay, so the pole here is actually very similar to a massive propagator. So under this poles, your double quantity can be factorized as a lower point quantity, which is actually a 2-point double copy form factor plus a 3-point gravity amplitude. And this factorization has a nature explanation in terms of new Feynman diagrams, which is given by the coupling between a graviton and this operator lag. Okay, so in the gauge theory, this because the operator is a color singlet, so it never couples to gluons. However, we know that gravity is coupled to everything, right? So this diagram is not so surprising. However, the introducing of this diagram is a bit intriguing. You turn the Spurious-Pole into a real physical pole. Although this is a very simple example, it's straightforward to generalize to high point form factors. For example, in this without loss of generality, in this 4-point form factor, you have these 8 diagrams. They can be classified into 3 classes. For example, consider this we define as the S channel because it's similar to the S channel to the 4-point amplitudes. The insertion of operator doesn't change your color factor, so it's given by the CS here. This is given by CTCU. So the form factor can be written in terms of these 3 terms, and we also impose a CK duality here. Namely, the numerator should all satisfy the same linear relation as color factors. So you can also solve this the requirement and find the unique solution for your numerator, CK dual numerator. And this is just some details related to some propagator matrix. And then, given this the CK dual numerator, you can make a double copy. And nicely, this can be written immediately written in a KLT double copy form. Okay. Of course, the subtlety here is that the gauge numerator has also Spurious-Poles, which become real poles after double copy. So this is the numerator concrete expression here. Just the detail is not important, but here these poles are Spurious-Poles in your gauge theory. Okay. So however, the double copy quantity not only preserves the Fonfie invariance, but also has a consistent factorizing property on these new poles. Basically, it will give some new diagrams that this graviton coupled to your operator lag. Okay. So here is just to show that the double copy of form factor is consistent, furthermore, this double copy reveals some hidden relations which just within the gauge theory, namely that your form factor satisfies some factorized relation at your Spurious-Poles. Okay, so this is also a very surprising fact. Normally, we only require that on physical poles it has factorizing behavior. So to give you a concrete 4-point example, one finds that when taking this Spurious-Poles, this combination factorized as a lower 3-point form factor times the 3-point amplitudes. Very interestingly, the left-hand side is almost the same as a well-known BCG relation for amplitudes. However, the right-hand side is no longer 0. Moreover, you need to take these constraints for your left-hand side. Okay. just to give a summary and outlook, so the form factor are important introducing physical quantities. And we have report some recent progress. The first is about a new CK dual solution, which contains surprisingly large solution space, even up to 4-loop order. And we also show that there is a hidden dual conformal symmetry for the form factor, which has also XP check up to 4 loops. And as a second part, we show that there's been making some concrete steps towards understanding the double copy of form factors, where this Spurious-Pole become real propagates in gravity. Besides, hidden factorial relation for gauge form factors are also found. Okay, so finally, I like to mention my brilliant collaborators, which is the Guanda Lin and Siyuan Zhang here. So Siyuan Zhang is a graduate student, and Guanda Lin actually who really take a major role in all these studies. He's only just got his bachelor degree this summer, and he's on the job market for a PhD program. Okay, so thank you very much for your attention. I will stop here.
Thank you very much for the clear talk. We have time for a few questions. First from the local audience, I guess.
Hi, that was really interesting. Maybe can you say a little bit more about the freedom in the numerator? So you had numerators with the Spurious-Poles, and then you showed that in fact you do the double copy, everything works and turns into real poles and so on. But what freedom do you have in the choices of these numerators?
Okay, so in the actually in our construction, this so I should in this construction we impose that the numerator satisfy all dual Jacobi relations. Okay, so the propagators should not be connected to the operator here. So and also for the solution we find, it's all have minimum requirement. We don't introduce a Spurious-Poles and also requires a minimum power counting behavior. In this way, we find a solution. And the reason that at least for our understanding is that for the form factor, there is a new type of this the general gauge transformation related to that you shift your position of your operator because it's a color singulate operator. So when you change the position of your operator, your color factor doesn't change here. Okay, so we in our CK dual construction, we don't impose the numerator should satisfy this dual relation for color factors. So that seems to give some more freedom for your numerators. Okay, and one can see that to cancel those free parameters, you must involve this the general gauge transformation related to the operator induced relations.
Yeah, so, thanks. Yeah, it's really great that this construction works even when you think it shouldn't work. Because it's Spurious-Poles. That's great.
Yeah. Also if you really want to make a double copy for this relation must be taken into account in your construction. Mm-hmm. You need to impose namely you need to impose further relation for your numerators to also satisfy this type of the color relations.
Okay. Let's move to the next question by Eric. I see you have a...
Yeah. Hi, gang. Thanks for a nice talk.
Hi,
so my question is, can you clarify a bit what checks you have done? So I suppose you have checked for one operator leg to some multiplicity, but have you also checked 2 operator legs in such situations?
Oh, that's I suppose you mean the form factor with 2 operators.
Yeah, I mean, so if form factor has 1 operator, but if you have 2 operators.
Yes. That's a very interesting question. We haven't done any concrete computation here, so that's a very interesting.
But just for 1 operator, to which multiplicity have you checked?
You mean what kind of operators?
No, sorry. If you have one operator, how many gluons, gravitons have you checked?
Okay. That's the right. So far, it's we know that for the Sudacon form factor, we have done the 5 loop solutions. And
no, sorry, I just mean tree level.
Oh, for the you mean for the double copy of the tree level?
Yeah, that's right. What multiplicity?
This we have been exhibit check up to I think 7 gluons.
Oh, okay. That's
so the double copy is works. So of course we haven't have a precise proof about this propagator, in particular this S factor here.
All right.
Yeah, we try to give a precise proof, but exhibit check has been done for the 7 points.
Okay, thank you.
Yeah.
Okay, next is Donald.
Thanks. Hi, gang.
Hi.
Thanks for a beautiful talk. It's really cool. I was just wondering, in the gauge theory, when you have these this issue of these spurious poles, did you think about including diagrams in the gauge theory that do have this spurious pole, like a propagator in that pole, but has a 0 numerator, and then an appropriate color factor? Now you'd be able to move things around, use generalized gauge symmetry to put a numerator there, and potentially have a a double copy where you don't, where the diagrams match on both sides. Normally the diagrams match. It's kind of interesting.
Yeah, that's an interesting proposal. Yeah, to maybe to answer the question that if you it's a problem here actually is highly depends on the propagator structure. So to solve this numerator, you need to first have, so this actually it's similar to the similar setup to consider this bi-adjoint scalar theory. You can define a similar the bi-adjoint scalar form factor, and it has the same I think here this same theta matrix here you can consider. The reason you have this kind of simple type of Spurious-Poles, this is like a massive propagators, is highly depends on your structure of this theta matrix. In your question, if you I'm not sure that if you including more diagrams, your theta matrix will become much more complicated, and I'm not sure that in that case that is a double copy. Yeah, you will have a nice double copy structure here. Probably you will have some quite ugly Spurious-Poles here, which has no real physical information even in gravity side. Yeah, but that's an interesting point to consider.
Maybe one last quick question by Hilbert.
Yes, hi. So I was
Hi.
wondering if you could comment a little bit more on this factorization of your gauge theories in the Spurious-Poles, like what is the intuition behind that new factorization, and what's the the physical meaning?
Yes, that's we try to understand better. So the reason that this we have this relation is because the double copy relations. I don't in our paper we have some more detailed arguments, but here you can see that your factorial property, okay, impose that this double copy quantity has this factorization also in terms of double copy of a form factor. And sometimes if you take a square root for both sides, okay, the double copy quantity becomes the form factor. And on the right-hand side, it becomes the factorization of the lower point form factor and amplitudes. So that's the reason that we discover these relations. But it's very interesting to ask further. As we know, it's very close to the BCG relation, and BCG relation has a nature interpretation like the string monodromy relations. Okay, so I think it would be very intriguing to answer whether there is a string generalization and such a Spurious-Poles would have some interpretation in terms of these string amplitudes, maybe some generalized monodromy relation from the string point of view. I think, but I don't have a concrete answer. very
thank you.
intuitive picture to answer.
I think we are now running a little late, so
Okay.
maybe we thank the speaker again
Thank you very much.
and
I'll
go to
stop
the next
sharing.